In this video, we're taking a look at the strengths of acids and bases, Ka, Kb, and strength versus concentration. So an acid is classified as strong or weak based upon how many of the hydrogens of those acids are being ionized. If we have a lot of ionization or complete ionization, like we see with hydrochloric acid and sulfuric acid, then that is a strong acid. But in the case of acetic acid, vinegar, or carbonic acid, where only part of those acid molecules are going to ionize and release hydrogens, then it is a weak acid. So we can get an acid dissociation constant, which will tell us about the amount of ionization that's happening. So we look at acetic acid, where less than 1% of the molecules actually are ionizing. We have a very low amount of hydronium ions, as opposed to the hydrochloric acid, again, which is going to be completely ionized. So we're going to get a lot more hydronium ions being formed. So they get to an equilibrium. So looking at the equilibrium constant, again, the products versus the reactants, we see that the hydronium ion and the conjugate base, therefore, that is formed as that hydrogen is released relative to the water that is there that's being dissolved into and the amount of acid that's left behind, that again, we get an equilibrium constant to give us a ratio of the products to the reactants. So when we have a very dilute concentration of an acid, then we can kind of ignore the amount of water that's there because the amount of water isn't really changing. So we're going to take our equilibrium constant, pull out the water of it, and that leaves us with this, our Ka. Because we're moving the water out, which really doesn't change in value and really doesn't affect how much water there is or isn't. You could add more water, and it's not going to change the amount of hydrogen ions that are being released. So therefore, we can take that out of this equation, and that gives us our Ka, the amount of ionized hydrogens or hydronium ions times the conjugate base divided by the amount of acid that remains, and that will give us a value which will give us an idea of how strong or weak an acid is. If you have a very small Ka, that's because you have a large number in the denominator, you have a lot of acid left over and very little ionization happening. A strong acid is going to have a large Ka because you get a lot of ionization, so you have a large number in the numerator, and therefore also a lot more conjugate base, and very little acid left behind. So bases work the same way. Bases that will completely ionize and release lots of hydroxide ions when they dissociate are strong bases, and ones that are only partially ionize and dissociate, give us very few hydroxide ions, are weak bases. And we can do the same with our equilibrium constant, except instead of now having our hydronium ion and our conjugate acid over the amount of acid left over in water, we now have our conjugate base with a hydroxide ion over the base and the amount of water. And again, the water isn't really going to affect the dissociation and how that relates. So we can take the water out and we get our Kb, which is going to be the conjugate acid times the number of hydroxide ions divided by how much base is left undissociated. So now let's look at how this strong and weak acids and bases relate to concentration. Concentration, again, is the molarity, the number of moles per volume, moles per liter of a solution. So it can be concentrated or dilute, and that has to do with how many particles are being dissolved in. It doesn't have to do with the strength, how many particles are ionizing. So strong and weak, again, has to do with how many ions are being released as that acid and base are put into solution. So you can have a whole mixture of concentrated and dilute and strong and weak. So you could have a concentrated solution that's made up of a strong acid, but you also could have a dilute concentration of a strong acid. You can have a concentrated solution of a weak acid, and you can have a dilute concentration of a weak acid. And it works the same way for the bases. So if you could have vinegar and dissolve it into very little water, well, you're going to have still the same amount of ionization happening. It'd be concentrated, but again, you're getting very few ions, so it's not going to be a very strong acid. At the same time, you could have very dilute, lots of water, dissolve in a little bit of hydrochloric acid, but it's still a strong acid because they're all going to ionize, but it's going to be a dilute concentration because you put very little hydrochloric acid into it. So we can take a look at this acid dissociation constant by looking at the molarity to begin and what amount of ions are going to be formed. So here we have a 0.1 molar solution of a monoprotic acid. It doesn't really matter what the acid is, but monoprotic tells us one hydrogen is going to be ionized when this dissolves into water. And when it gets to its equilibrium, we have a hydrogen ion concentration of 1.34 times 10 to the negative third. What is our Ka? So let's list out what we know and what we don't know. And we know that we we have the 0.1 molar solution to begin, and then it gets to equilibrium, and we have 1.3 times 10 to the negative third H plus ions when it gets to equilibrium. What is our Ka? So to get Ka, we need the number, our concentration of our H plus ions times the conjugate base divided by the concentration of the acid, again when we get to equilibrium. So we got to fill in a couple holes here. The easiest one to first fill in is the conjugate base. Since it's a monoprotic acid, we know that for every hydrogen that is being ionized, we're also getting one conjugate base, so their concentration is going to be exactly the same because it's going to be a 1-to-1 ratio. If it was a 2-to-1 ratio, then we'd only be getting half if it was diprotic. Or if it was triprotic, we'd be only getting 1/3 the conjugate base. But in this case, being monoprotic, they're going to be exactly the same. And then to figure out our acid, again, since it's monoprotic, for every one hydrogen that is being ionized, then therefore there's going to be one molecule of our acid that is going to be ionized, so we can subtract the amount of hydrogen ions that are being formed from the amount of acid we had to begin, and we find that there's 0.0986 molar concentration once it gets to equilibrium. So let's go ahead and plug in and find our value for Ka. So we have the 1.34 times 10 to the negative third for our concentration for our hydrogen ion. We also have that same for our conjugate base, divided by the 0.09866 molar of the acid once it's still there at equilibrium, and we find our Ka to be 1.82 times 10 to the negative fifth, and again, a very small value like we'd expect looking at the numbers of how much dissociated versus how much remained as acid, and therefore we know it's a very weak base.